I got embarrassed and humiliated.
When you're holding a scissor, you're laughing.
You think
Did you get it? I didn't calculate.
so? If you have
Oh wait, I had wrote down a measurement.
All right, so let's talk about this question. I'm also recording for other people who are absent. I think there's few absence today. But basically, we start with this paper that in matrix that how long is this paper is? What's the length of this paper originally? 27.9. Okay, what's the other side? 21.7. So let's reinstate the problem. The problem was we give you this piece of paper. It's just normal letter size paper. It has 27.9 centimeter on the, I don't know, this width or length. What kind of math teacher? I don't even confuse that. That's length or width?
Which one?
What?
The longer one.
That's what we were talking about. It's like,
Yeah.
and then
Longer
Oh,
one
no.
line.
width is
Well, the
25.
side one,
multiplied.
the side is width, the long one is length.
Yeah.
That's what
Because like
it is.
L and long, so like it's got. Wait, what did you do?
I don't know.
You're taking advice from me.
But like how
Yeah,
long
you
is it?
I got-
All right, so what we're gonna do, we're gonna take this paper and we're gonna cut out each square corner on the side, and we're trying to form the biggest open top rectangular prism. So what happened is, let me talk, please. You cut off each corner; they have to be exact same size. So, and like Laura and then somebody here, they cut out different. They didn't cut off a square.
It's the same size.
Same size, thank you.
No, look at the edge. Fold it upward. Are they same height? Are they same height? You cut it. You cut it. It wasn't. It wasn't before.
Literally did it. She literally did it. So what are you saying?
She's dying. Okay. So then you're gonna find the biggest open top box. Now, there was some theory in this class. There was some theory that from Amara's group, Amara's group start with cutting the smallest rectangle. They're trying to find the biggest base area, and they trying to find out are they gonna be the biggest. Now, on the same group, Leah decided to cut out the biggest square that he can possibly think of, and to try to find the biggest volume of the rectangular prism, but end up to be the smallest.
So there's no winner.
So the answers must be somewhere in between, right?
Maybe halfway.
So, and a lot of different ideas pop in. I think Luke them have trying to use the math. What do you guys come up with?
Nothing.
Nothing?
Let's see your prism.
3 as the
3 is a height.
Yeah.
Okay, so they come up with 3. Anybody come with a different number?
Yep.
4.7. Okay, anybody come up with a different number?
6.6.
6.6. But which one's bigger? 4.7 is bigger or the 6.6 is bigger?
Is it not?
I recalculate.
Oh, you recounted.
I think this is because you're trying to cheat that cut off that.
That's not true. I didn't cut it off. I have no idea.
Can you take away the scissor? When she raised her voice, my heart rate go up. With a scissor, of course. What just happened? Okay, so this so you gotta understand that this side versus this side. So what we're gonna do is we're gonna assume this side is x. Is that okay? Is this okay?
Yes.
Now, if I fold it upward, what's the volume? Volume of rectangular prism. Think about it. Hey, volume of rectangular prism is length times width times height. Is that okay? Now, obviously, you can cut this big. That's what Leah did. Kind of try to cut it really big, right? And if you fold it upward, you end up getting a really skinny rectangular prism and really tall. She make a record on the tallest rectangular prism. Not a big value, but she did make a record. That's fine. And Maria cut out like something like really small, like at least that's on her paper. She folded a little bit small. And she says, well, which one's bigger? Well, we don't know, right? Until you actually do a calculation. So we know that we have to do it with the calculus. So we know the height of the box in terms of x is going to be what? What is the height of the box? If you fold it upward, what is the height?
1 centimeter.
X. Because you fold it upward, that's the height of the box. Does that make sense?
Yeah.
Numerical value.
Now, what will be the length? Length is going to be what? 27.9. It's minus x? Minus 2x.
Oh, because you couldn't choose that.
Here, there's the.
Because you cut off on both sides, right? You cut off on both sides. Is that okay?
Yes.
And what will be the width? I think it's 21.6, but okay, 21.7 minus 2x. That's fine. Yeah, according to the paper, it's 21.7. So different class have different measurement. So this one's going to be length, width times height. So volume is equal to x times 27.9 minus 2x times 21.7 minus 2x. Because you cut off one on each side, so the x is folding upwards. So that's why I was telling Luke, when I come by and I say your calculation, something is wrong, and you guys didn't listen to me or did not react, but that's okay. This is all part of the learning process. So we got this volume equation, and this is the calculus. Well, this is actually the algebra, actually. You learn this at algebra if the algebra teacher is good. If. So volume equal to the x, which is the height, and not subtract 2x and subtract 2x. Now you got a volume equation. Now what you're going to do is, we're going to take this. We say, hey, I can distribute it, and what do we do with calculus? What do we do? Take a derivative. Good job. Gia is like, derivative, yes. So what happens if you find a derivative? You can find some number. What kind of number is that? What?
Slope.
Well, yeah, but you can find,
Increase.
what kind of? Critical number.
Oh.
Remember, on a critical number, it has a possible maximum and a possible minimum, right? So we're looking for the possible maximum. So this is what we do. But it turns out this question doesn't require calculus, but with calculus, it's going to be easier. So this is the actual graph. Now, I want you to take out a graphing calculator, graph this function, x times 27.9 minus 2x, 21.6 minus 2.6. Now, I want to talk about something else. It's called physical domain. Now, I remember I teach a few years back at, Laura, put your phone away.
Oh, this one.
Oh,
You didn't take out the graph.
okay. Because I feel like she's texting. Were you not?
She's number one gaslighter. I'm not gonna lie.
Why would I be texting mid lesson?
I'm kind of sus.
No way you just said that.
Maybe always says that.
Okay, so then you graph this function and you find out you see a straight line. How does that straight line help me? So that's first thing, let's talk about something. I want to make sure that there is actually something called physical domain. You might want to write this down. Physical domain. What is a physical domain? Now, physical domain is on the shorter side, because imagine if I cut the longer side, if I decide a physical domain, if I cut this is fine, right? This is what looks like kind of like Dia's box. But if she cuts a little bit bigger, then it's going to be no more box to be with, right? So she cut like pretty big. She could like try to cut up like this. And so her box is very, very tiny and skinny. But she cannot cut more than this part, because 21.7 is actually known as a physical domain, except sort of. Is 2x is less than 21.7. Why is 2x? Because two-sided x, that's how much you can cut. You can cut the maximum as 21.7 is what? 21.7 divided by 2 is what? 10.85. So this is actually physical domain. That means the domain has to be between 0 to 10.85. You can cut anywhere between 0 to 10.85. You cannot cut more than 10.85 because you have no more box after that. No more box. Because you cannot cut bigger than that. Does that make sense?
Yes.
So the reason why I talk about physical domain is after the second year I teaching calculus, after the second year, I was teaching a group of very young students, like 8th grade. They were doing calculus in the room. It was in summer program. I established summer program. I tried to teach a bunch of very young kids about calculus concept. And those people are very, very, like Jonathan is one of the smartest kids in there. So Jonathan was like always answering the question. And I always allow parents to be in my room as well when I was teaching them. So the parents come, there was one time his dad coming along with, I was teaching optimization. His dad raised his hand, says, hey, would you mind for me to introduce this topic, optimization? This is my favorite topic. And I didn't say no to him because I always learn to like make sure you respect other people, even though like in my mind I was thinking like, who you think you are? But luckily I did not do that, luckily, because he went out in front and he started talking. He's like, well, my name is Dr. Wang. Doctor. So obviously it's much better title than Mr., right? So Mr. Ye is like nothing compared to Dr. Wang. So Dr. Wang went up there and he started talking. He's like, well, I'm Dr. Wang, by the way. I'm a UCF professor.
Ooh, we got you.
I know, right? He got me there.
Yeah.
Luckily, I did not insult her in any
Yeah.
way. Like, so he's a Dr. Wang, and he's a civil engineer professor in UCF.
Oh, if you had clock.
Yeah,
oh,
actually
dang.
clocked like wow.
Yeah, then that would be bad. Luckily, I was smart, so never underestimate a lot of people. So, so he says one thing about engineering. The only thing that a lot of time we do in math, we only worry about mathematical domain. So, for example, the question on the board, x times 9 minus x squared, domain is between -3 and +3, and that's mathematical domain. But in this case, the domain is the actual piece of paper. You cannot cut more than 10.85 because you have no more box. So that's called physical domain. So as an engineer, which is like him, they need to recognize physical domain rather than mathematical domain first, because physical domain is what's restricting you to building this product. Now, with that being said, we come up with the equation, and we also know the physical domain. And what we're going to do is we're going to go into the graphing. We go into graphing here. We says x times 27.9 minus 2x, 21.6 minus 2x. The output is going to be the volume. The output is going to be volume, but we see a straight line. It's like, well, what's going on? So we're going to click the wrench on the top corner, right-hand corner. If you click the wrench, and we're going to go to x-axis, we're going to say, well, we need to worry about the physical domain. So the physical domain is between 0 to 10.85, but I need some slack room. I need to see a little bit back. So I'm going to see 1 unit to the back, so it's -1 to, say, 12. Why 12? Because now I see 2 lines. This volume equal to 0, this volume equal to 0. So then you say, okay, well, I need to see the output. Well, most of you guys already found out the output is going to be either 800 or 900 or 500 or even 1000, right? So I'm going to go click the Y value. I'm going to go all the way to probably maximum. Let's try like 500. Like you don't see enough for the graph, right? So we're going to go to maybe 1500. Now, if I go to 1500, I see this nice, beautiful graph here that has any volumes, any volume of how much you cut. Pay attention. Did anybody cut 1 centimeter? If you cut 1 centimeter, the output is going to give you exactly, if my hand can be steady. I cannot. So it'll be 503. My hand is shaking. If you cut 2 centimeter, it's going to go up higher. 843, which is that's what Austin got. If you cut 3 centimeter, it's gonna be 1022, right? The maximum is right here. It's 4.025.
So we won.
96.
So we won. That was my height.
We get a prize.
Basically, I mean,
Oh yeah,
an
can
A
we
in
get a
the
prize?
class.
Did you get the highest?
You got the
Yeah.
She got the highest.
Our group.
It was a good effort.
Yeah, group effort.
Okay. I'll think about it. All right.
10 extra credit points.
So this is 0.1. So 1082.59, that's your maximum height. Now, this one I didn't not use calculus. How does the calculus come in play? Because I can distribute this and just take a derivative of power rule. And if you do that, look at a graph of a v prime of x. Now, I'm not going to show you the thing. I'm going to show you v prime of x, which is, remember, we had to analyze in the graph from before. Where does maximum happen? The maximum happen is when f prime of x went from positive to negative. Remember on your last test? So remember, this is a positive. This is negative. I here is a 4.025.
So that's when it stopped becoming bigger.
Yes, that very good.
Observation.
Yes, observation. Thank you for finishing my sentence.
Now it's negative and you can't be negative.
Well, it's gonna decreasing. The volume is gonna be negative. So as the volume start decreasing, until this point, it's gonna be a create minimum, right? But the problem is 12.47 is past the physical domain. So it doesn't really matter there. So, but if you look at origin function, you see that at 4.02, it's a maximum. See how they cross the x-axis at 12.47? It becomes a minimum because I here is 12.47, only cross that.
But what about when it goes back up? Does it ever go back up?
Yeah, but the problem, it did go back up. And not only go back up, it go with higher, right?
Yeah, so
But then you have no more paper to cut. So your physical domain is happen to be between 0 to 10.8. So that's after 10.8. That doesn't matter anymore. That's what physical domain matter. Okay.
that was good. That was good.
What do we do with the box?
You can keep it or trash it or put it in the bag. Don't leave it on the table though.